Hello, everyone. I was looking through some past exams that I've done, some calculus past exams I've done, and I came across a particularly interesting question. I spent some time thinking about it and not exactly sure what I should be doing. I eventually realized that there were actually lots of different ways of doing this particular question, and I wanted to share some of my thoughts uh, on this question with you. So the question was as follows. We're looking at series. So we've got a sequence of terms, in this case, the natural logarithm of 1 plus 3 divided by n, and we're adding all of these up. And the question before us is this: does this series, when we take the limit, does this series converge or does it diverge? Now, I found four different methods that we can use to treat this, and I want to go through some of these with you now. The first method that I thought of to use this was with Taylor's theorem. So what motivated me to use Taylor's theorem? Well, the thing is, this question that we're dealing with, the natural logarithm of 1 plus 3 on n, I can spend some time thinking about what I'm actually trying to achieve here. I'm trying to get a solid understanding of these terms, the natural logarithm of 1 plus 3 divided by n, for n particularly large. When n is large, this is where most of the important stuff happens. Well, when 3 divided by n is when n is large, that means that 3 divided by n is really quite small. And so we're looking at the natural logarithm of 1 plus a really small number. Do we have any tools that we can use that will allow us to gain some insight into what these terms are for n really large? Well, it's Taylor's theorem that will help us do this. So Taylor's theorem, I've got this written over here. If f is differentiable at 0, for example, then we can say that f of x is given by its linear approximation at 0, which in this case is f of 0 plus f prime of 0 times x, plus e of x, which I'm going to call an error term. We don't know too much about this error term, except we do know that the absolute value of this error term vanishes to second order for small x. So I've written that as the absolute value of e of x is less than or equal to c times the absolute value of x squared. All right, well, let's get to applying this theory to our question here. So for small x, what can we say? Well, the natural logarithm function, 1 plus x, is actually differentiable at x is equal to 0. We know that the derivative of the natural logarithm of 1 plus x is 1 divided by 1 plus x. So when x is equal to 0, the derivative is just equal to 1. The function itself is equal to 0. The first derivative is 1. And so that means that using Taylor's theorem, we can write that the natural logarithm of 1 plus x is just equal to 1 times x plus an error term, e of x. We don't know much about e of x, but we do know that its absolute value is controlled by c times the absolute value of x squared. So this is what happens for small x, but remember, we're looking at natural logarithm of 1 plus 3 divided by n. So if we set x to be equal to 3n, what we can conclude is that the natural logarithm of 1 plus 3 divided by n is going to be equal to 3 divided by n plus e of 3 divided by n. Now remember, what we're doing is trying to evaluate the convergence of the sum of all of these, and we've expressed this as this plus this, which means we've now essentially broken this problem into two. Let's see if we can get some information about the sum of all of these terms and the sum of all these terms. Well, it turns out that the second of these is a bit easier to deal with. Again, we don't know much about the e function, but we do know that e of x is bounded by some constant times c of x, some constant c times x squared. And so that means the absolute value of e of 3 divided by n is bounded by that same constant c multiplied by the square of 3 on n, which in this case is 9 on n squared. So the absolute value of this thing is bounded by a constant divided by n squared. So when we sum all of these up, we know we're going to get convergence. And what I'm using here is the p-test. I'm using the p-test, which says that if I sum up a constant divided by n to the power of p, and that number is bigger than 1, then what I get is something that converges. And so therefore, what I can conclude is that the sum from n is equal to 1 up to infinity of e of 3 divided by n, this sum is actually convergent by the p-test. And I'm also using the comparison test here. I'm comparing my e function to a constant divided by n squared. Okay, so that's one of the two terms dealt with. We want to deal with this, and we also want to deal with this. I know that this second term has a convergent sum. But what about the first term? The sum from n is equal to 1 up to infinity of 3 divided by n. Well, again, we can just use the p-test. The p-test says that we get divergence if p is equal to 1. And so that means this thing diverges. So the sum we're trying to deal with, the sum of all of these terms, ln of 1 plus 3 divided by n, well, that's equal to the sum of something which has a divergent sum as well as a convergent sum. Something we know about sums and series is that they're linear, and we can conclude information about the convergence or divergence of the sum of two series based on the divergence or convergence of the series by themselves. In the case we've got one thing that converges and one thing that does not converge, the sum also diverges. And so the conclusion we make is that this particular sum here, ln of 1 plus 3 divided by n, this diverges. We're dealing with a divergent sum here. All right, so that was the first method I wanted to go through with you. There are 3 other methods I want to go through with you. And as we go through these methods, hopefully we'll find that all of these things, no matter what method we use, we should still get a divergent sum. Let's have a look at the next method. The next method is limit comparison. So remember, what we're trying to evaluate here is whether or not this sum here, the sum from n is equal to 1 up to infinity of ln of 1 plus 3 divided by n, we want to know if that thing converges or diverges. Now, this method is limit comparison, and the limit comparison method is described here. And it says this: if you're looking at two sums, a sum of an and a sum of bn, and you look at the ratio of the individual terms, and it turns out that this limit exists and happens to not be 0, then that means that the convergence of one of these will imply the convergence of the other. And so if an has a convergent sum, then bn has a convergent sum, and vice versa. On the other hand, if one of them diverges, then they're both going to diverge. And so, in order to use limit comparison for this particular question, I need something sensible to compare my function with. I'm dealing with ln of 1 plus 3 divided by n. Is there something sensible I can compare it to? Indeed, there is. And our hint actually comes from the previous method. We saw that 3 divided by n was actually the key thing that made everything diverge. And so maybe we can just compare to that directly. What we're going to do is make a comparison with 3 divided by n. So how does limit comparison work? Well, we're interested in the ratio of these two things. We're interested in the ratio of ln 1 plus 3 divided by n, and we're interested in dividing that by 3 divided by n. Let's again think about this in terms of x's. What I'm interested in is this limit here. The limit as x approaches infinity of ln of 1 plus 3 divided by x divided by 3 divided by x. Eventually, I'm going to want to do this with n, a discrete limit, But for the moment, I'm going to use a continuous limit, and the reason is because I really want to use L'Hopital's rule. L'Hopital's rule really needs continuous limits. So the limit as x goes to infinity of ln of 1 plus 3 divided by x divided by 3 divided by x. L'Hopital's rule. Can we use that? Well, L'Hopital's rule says that if we're looking at the limit of a ratio of two things, then what that's going to be is the same as the limit of the ratio of the derivatives if this limit exists, and if the limit as x goes to infinity of f of x and g of x, if these are both going to be 0. So if both of these functions have a limit which is 0, then we can make statements about the limit of the ratio based on the limit of the ratio of derivatives. So we can use L'Hopital's rule here because as x goes to infinity, 3 on x goes to 0. And so ln of 1 plus 3 on x also goes to 0 because this is just going to ln of 1. And so L'Hopital's rule is actually applicable here. And what we can say is that this is the same as the limit as x approaches infinity of, well, we need to calculate the derivative of the logarithm function minus 3 divided by x squared times 1 plus 3 divided by x. So that's the derivative of the natural logarithm. And then we've got to divide by the derivative of the bottom, which is 3 on x squared. So remember, the derivative of the logarithm is 1 divided by whatever's inside the logarithm, which in this case is 1 plus 3 on x. But we can't forget about the chain rule. We have to multiply all of that by the derivative of what's inside the logarithm, which in this case is 3 divided by x squared. All right, what do we notice about this limit? Well, we get a lot of cancellation. The x squareds cancel, the 3's cancel, the negative signs cancel, and we're left with the limit as x goes to infinity of 1 divided by 1 plus 3 on x. Well, this is just going to be equal to 1. That's a nice and straightforward limit. But this, of course, means that since the continuous limit is 1, the same is true for the discrete limit. So as n approaches infinity, the natural logarithm of 1 plus 3 divided by n divided by 3 divided by n is also equal to 1. But this is quite exciting because now when we're in a position to use the limit comparison test, I've got a sequence an and a sequence bn. I know that the ratio is convergent to 1. And so that means if I can make some conclusions about the sum of this, I can make conclusions about the sum of this. Well, I know that the sum as n is equal to 1, the sum from n is equal to 1 up to infinity of 3 divided by n, this is divergent, typo there. This is divergent by the p-test, and so therefore, by the limit comparison, the same is true for ln of 1 plus 3 divided by n. So that's great. This sum is again divergent using a different method. All right, that's limit comparison. You may notice that Taylor's theorem approach and the limit comparison approach, they work quite similar. Let's try and have a look at some methods that are quite different. The next method we're going to look at is the telescoping series method. So how does this method work? Well, the way to get this method to work, remember we're trying to look at the convergence of the sum of ln of 1 plus 3 divided by n. In order to use theory of telescoping series, that means I need to express my series as a telescoping series. A telescoping series is any series where you can express each individual term as a difference of adjacent terms of another sequence. Because when that happens, the theory of telescoping series gives you a very nice picture about what the infinite sum actually is. It's just the limit of the original sequence minus the first term. All right, so what we really need to do is somehow express ln of 1 plus 3 on n as a difference of adjacent terms of a sequence. Can we do that? What do we know about this particular function? Well, ln of 1 plus 3 divided by n. Remember, what I'm trying to do is express this as a difference. So what would be really helpful is if I could express this as a difference. Well, using log laws, I know that I can do it if what's inside is a ratio of something. So what I'm going to do is make what is inside the natural logarithm a ratio. 1 plus 3 divided by n, that's the same as n plus 3 divided by n. But I'm now in a position to use my log laws. ln of n plus 3 minus ln of n. So this is good, but it's not quite what we want. And the reason it's not quite what we want is because, well, this doesn't really look like adjacent terms in the sequence. We could say our sequence is just ln of n, but we would really want ln of n plus 1 here, not ln of n plus 3. How can we fix this? Well, we can do a trick that maths lecturers love to use all the time, the old plus and minus trick. I'm going to add and subtract terms to this expression until it looks like what I want it to. So what I'm going to do is add in an ln of n plus 2 and an ln of n plus 1. But of course, I have to subtract them since I've added them. And so I'm going to subtract them down here. ln of n plus 2 plus ln of n plus 1. Oops, that's a minus. Minus ln of n plus 1 minus ln of n. And so what you may notice is that we've now actually achieved what we set out to do. We notice that if we let this thing over here be an, and this thing over here, well, that's then going to be an plus 1. So this whole series can be expressed as a telescoping sum, the sum of an plus 1 minus an, where these an terms are given by ln of n plus ln of n plus 1 plus ln of n plus 2. Great. Now I'm in a position to use the theory of telescoping series. The sum from n is equal to 1 of infinity of an plus 1 minus an, that's just going to be the limit of n, limit of an as n goes to infinity minus a1. But if we look at an, ln of n plus 1, ln of n plus 2, all of these things are getting larger and larger as n goes to infinity. And so therefore, this limit does not exist. And so the whole series is divergent, same as what we already found. So this was done using the nice trick of telescoping series. Now there is one more method I have to show you that we can use to conclude divergence of this particular sum here. This is not one I would recommend. It's the most technical, but it also uses perhaps the cruelest test for series that we have available, the integral test. What does the integral test tell us? Well, it's a way of turning a sum into an integral. So the setting is as follows. If we've got a function, a continuous function, that happens to be decreasing and convergent to 0 as x goes to infinity, then the discrete sum of fn from n is equal to m up to infinity, whether or not that converges or diverges is determined entirely by what the integral of this function is doing from m up to infinity. Okay, so we're looking at the sum from ln of 1 plus 3n from n is equal to 1 up to infinity. So that means we're interested in looking at this function here, ln of 1 plus 3 divided by x. Well, the good news is that if x is bigger than 1, this function is decreasing. It is continuous. And it is also convergent to 0. This is great because it means that in order to work out whether or not this converges or diverges, it suffices to look at this integral here and see if that converges or diverges. Well, you might be a little upset with what's happened so far because, well, ln of 1 plus 3 on x, that looks like a particularly challenging integral to perform. How can we possibly do that? Well, there's one more trick up our sleeve that we need, and it's integration by parts. So if you happen to be integrating a product of two things, let's say that one of them is a function u and the other one is the derivative of a function v, then that can be expressed by evaluating the product of u and v between the integral bounds, and then subtracting an integral of the derivative of u times v. Okay, well, this isn't obviously helpful because the integral of ln 1 plus 3 on x, that's just one term. That's not a product, or is it? Well, it is a product with a silly trick. And the trick is you imagine this whole thing just multiplied by 1. So u is going to be the function in question, and we're going to multiply it by 1, which we're going to call v dash, the derivative of a function v. Well, if v dash is equal to 1, that means we can say that v is going to be equal to x. And if u is equal to the natural logarithm of 1 plus 3 divided by x, that means the derivative of u, which we already computed back up here, the derivative of u, which we've already computed, is equal to minus 3 divided by x squared times 1 plus 3 divided by x. Well, we're now in a position to do our integration by parts, so let's get on with it. The integral of 1 up to infinity of ln of 1 plus 3 divided by x dx, this is what we're most interested in. Now, what does it mean to integrate to infinity? Well, the only way to make sense of that is with limits. So the limit as t goes to infinity of 1 up to t of the exact same thing. And now we're going to use integration by parts. This is equal to the same thing, the limit as t goes to infinity. But now what we can do, integration by parts, well, looking at our formula over here, u times v evaluated at the upper bound minus u times v evaluated at the lower bound. So that's going to be t, because remember the function v is equal to x, t times u, which we've said up here is ln of 1 plus 3 divided by x. So that becomes a 3 divided by t, minus the same thing, except we replace t with 1. Well, 1 times ln of 1 plus 3 divided by 1, which is ln of 4. And then the integration by parts, we subtract the integral from 1 up to t of minus 3x on x squared 1 plus 3 divided by x dx. Because remember, what we've got to put here is u dash times v. So that's all that's going on down here. Well, continuing on and simplifying a little bit, the limit as t goes to infinity of t times ln of 1 plus 3 on t minus ln of 4 minus, I won't integrate yet, I'll just simplify, cancel some of the x's. What I end up with is 3 divided by x plus 3 dx. Now I think I actually want to compute this integral, t ln of 1 plus 3 divided by t minus ln of 4. Now, an antiderivative for x plus 3 is ln of x plus 3. So using the fundamental theorem of calculus, this becomes 3 logarithm of t plus 3, and then subtract 3 times the natural logarithm of 4. So this guy became this guy down here. Okay, well, let's compute this limit. T times ln of 1 plus 3 divided by t. Well, it turns out that this particular term doesn't really matter too much. The important thing is that this term is going to be positive. So this is positive, this is constant, this is also constant. This term over here, this is clearly going to plus infinity, the natural logarithm of t plus 3, as t is getting quite large. So this whole limit is divergent. So that means that this integral here is divergent, and so therefore, by the integral test, this sum is also divergent. This sum over here is divergent. 4 different methods for the same series. All of them can be used to demonstrate that this thing is divergent. So that brings us to the end of what I wanted to talk to you about today. I hope you had fun learning about different series methods.